Picture an F1 pit stop. The car roars into the box. 2.1 seconds later, 4 tires are changed and it's gone. If a single mechanic hesitates for even half a second, the lead is lost. The race is over. Well, that level of high-stakes pressure, that's exactly what sitting the Cambridge IGCSE Physics 0625 exam feels like. In that exam room, timing and precision are literally everything. You don't have time to second-guess your data, and a slow reaction to a complex curve, that's going to cost you the grade. Okay, let's dive into this. Take the classic parachutist speed time graph, for example. A specific curve like this is exactly where your grade boundaries are won or lost. If you encounter this curve during the exam and hesitate for a mere 3 seconds, just trying to remember if the gradient represents speed or acceleration, well, that is your loose tire in the pit stop. It costs you time, it drains your confidence, and it leaves valuable marks right on the table. And you know what? The examiner's reports showed the exact same loose tire mistakes destroying students' scores year after year. We're talking about missing your units, rounding your numbers way too early in multi-step calculations, and writing those super vague explanations. Or worse, making graph axis reading errors, confusing your independent and dependent variables, and writing conclusions that the data simply does not support. This right here is exactly why ordinary revision and textbook memorization completely fail you. Examiners will mercilessly deduct points if you lack surgical precision in your answers. Let me show you exactly what that lack of precision looks like. Consider a classic, really flawed student answer. Speed goes up, then down. Now this gets 0 marks. It's conversational, it's vague, and frankly, it's not physics. Now compare that to an improved top-band answer. Speed increases, but acceleration is lower, reaching terminal velocity. Do you see the huge difference there? We're using precise command words and extracting exact physical behavior from the changing shape of the curve.
Now, what's actually really interesting here is the hidden physical context. In just a moment, I'm going to reveal the exact examiner clue that completely flips a 0-mark confused answer into a full marks bulletproof response. It's a specific physical trigger that literally changes how you look at every single graph. But before we get to that clue, you need the master framework to understand exactly why it works. So here is your 4-step surgical framework. This is the exact sequence you need to construct an absolutely unbreakable response. Step 1, identify the concept. Are we analyzing speed, distance, or acceleration? Step 2, extract the evidence or data directly from the graph. Actually read the numbers off those axes. Step 3, apply scientific reasoning. Ask yourself, why is the line curving? What forces are acting? And finally, step 4, lock it in with examiner wording. You absolutely must use the exact terminology the Cambridge mark scheme demands. Concept, evidence, reasoning, wording.
And this brilliantly illustrates our first quick win. To put this framework into action, you need a translation key for extracting data, and this summary table is your ultimate tool for motion graphs. So if you have a distance time graph, the gradient is equal to your speed. A downward slope just means returning toward the start position. But consider the speed time graph. Here, the gradient is equal to acceleration. A downward sloping line means decelerating. A horizontal line, that means no change in speed. You're moving at a constant speed, not stationary. And the area under the curve is your distance traveled. You've got to memorize this translation key.
All right, let's actually apply this framework to the first leg of the parachutist jump right from points A to C. At A, she starts to fall. Step 1, concept, speed and acceleration. Step 2, evidence. The curve goes up, but the gradient flattens. Step 3, reasoning. Well, air resistance is increasing against her weight. And step 4, examiner wording. Speed increases. She accelerates. At B, the speed is still increasing, but more slowly. The acceleration is lower. Finally, at C, the gradient is totally flat. The exact examiner wording required here is, she reaches terminal velocity. The acceleration is 0.
Okay, now I'm turning this over to you for an interactive challenge. Think about the downward sloping line starting at point D, curving through E and F, all the way to the landing at G. I want you to pause and predict right now. Mentally formulate your answer using our 4-step framework. What exactly happens from point D to point G? And remember to use the physical context here. She just pulled her parachute open after 28 seconds.
All right, let's see how your answer stacks up against the examiner-style correction. The core rule here is that a negative relationship is a downward sloping line. At point D, the speed decreases rapidly. Your examiner wording absolutely must be, this is a high deceleration. At point E, The curve flattens out slightly because the speed is decreasing more slowly. Therefore, the deceleration is lower. At F, we hit a horizontal line again. This is a new lower constant speed, which means it's a new terminal velocity and acceleration is 0. Finally, at G, she hits the ground, a rapid stop, meaning a large deceleration.
You're doing great, but the stakes are getting even higher now. Let's tackle question C from the exam paper. Spot the error in this student's claim. The parachutist traveled at 5 meters per second for 35 seconds. Think about the horizontal line indicating 5 meters per second. If you just glance at where that flat line begins and ends, you might fall for one of the absolute most common axis reading traps in the entire syllabus. So the crucial point here is the correct answer is actually 25 seconds. Why? Because the parachutist reached the 5 meters per second speed at the 35-second mark on the x-axis, and they maintained that speed until the 60-second mark. 60 minus 35 equals 25 seconds. The student who wrote 35 seconds just looked at the start of the line, saw the number 35 on the axis, and literally stopped thinking. You have to extract the data completely and accurately every single time.
So, we've successfully tuned up your motion graph strategy. But remember, data is only half the battle. If a single graph can hide this many traps, what happens when you step into the practical investigation room where you have to design the experiment entirely yourself? Are your physical concepts truly bulletproof, or is your next loose tire waiting in the lab? That's exactly what we're covering in our mandatory next lap, exploring the most dangerous traps by question type. You literally cannot afford to miss it. Subscribe to our YouTube channel, Ace the Exams at Ace the Exams IGCSE, to excel in your Cambridge examinations. Seriously, is your experimental design ready for the pressure test? See you in the next explainer.